Okay, so today, I will present the Photonic 6G wireless communications. Go to background. This slide shows the history of mobile wireless communications from 1G to 6G. Technology evolutions occurs every 10 years by increasing the wireless carrier frequency for the high-speed, large-capacity wireless communications. The present 5G use wireless carrier wave up to 28 gigahertz, which is a millimeter wave. The next 6G is starting at 2030 will use the carrier wave over 300 gigahertz, so which is a terahertz wave. However, there are still two technical challenges for 6G. The first challenge is the technical limitation of wireless electronics. Until 5G wireless electronics have been widely used. However, in the 6G, such a wireless electronics may face a technical limit of electronics, such as low signal quality and increased signal loss. Therefore, there is a need for the paradigm shift beyond the upper frequency limit of wireless electronics. The second challenge is the technical gap between optical and wireless communications. The present ICT is achieved by a combination of optical communications based on the photonics and the wireless communications based on the electronics. In this case, at the connecting point between them, the signal conversion between optical and electric signal is required, resulting in the generation of time delay. Until 5G, such a time delay is negligible. However, in the 6G, the ultra-low latency is strongly required. So in this case, time delay caused by signal conversion, we cannot ignore. So therefore, the seamless connection between the optical and the wireless communications are required. These two technical challenges arise from use of electronics in wireless communications. So if so, we can achieve the 6G by photonics in place of electronics. These two problems will be overcome. We define the 6G boosted by photonics as photonic 6G or P6G. Key of photonic 6G is optical frequency COM or OFC. OFC is composed of a series of frequency spikes regularly separated by a constant frequency, like here. OFC possesses both characteristics of the narrow line width and broad spectral coverage together with a constant frequency spacing. The most important characteristics of OFC is given by this equation, in which the nu m is optical frequency of m order COM mode. FCO is the carrier envelope offset frequency, FREP is the frequency spacing, and M is the number of OFC mode. Since FCO and FREP are photonic radio frequency signal around several tens megahertz, this equation indicates a coherent link of frequency between optical frequency and electric frequency. For example, if the FREP and FCO are phase locked to an electric frequency standard by laser control, uncertainty of the frequency standard can be transferred to nu m based on this equation. In this case, the OFC can work as an optical frequency ruler secured by the electric frequency standard. Recently, the optical frequency standard with a much better performance appears, such as optical lattice clock. In this case, if the nu m is phase locked to the optical frequency standard by laser control, excellent uncertainty of the optical frequency standard can be transferred to electric signal of FREP based on this equation. So in this case, the OFC can work as a frequency converter or frequency gear from optical frequency to electric frequency. So such a frequency gear can be used for generation of ultra-stable electric wave in R wave, microwave, and millimeter wave. For 6G wireless carrier over 300 gigahertz, how we can further increase the FREP of OFC? The answer is given by micro-resonator, optical comb, or micro-comb. This slide shows the technical evolution of OFC sources. The first generation is a Titan sapphire laser comb with a bulky, complicated, and expensive setup. The second generation is a fiber comb with a middle size, enabling the turnkey operation. The third generation is a micro comb. Key of micro comb is a micro ring resonator made of silicon nitride optical waveguide. When the CW laser light is cut into the micro resonator, the stable solitone comb can be obtained. Micro comb benefit from mass production possible with a semiconductor process, small, cost-effective, simple aspect, and high compatibility with the silicon electronics and silicon photonics. Therefore, a micro comb can give the versatility to OFC, so which is lacking in the previous OFC sources. Furthermore, since the cavity size of micro comb is largely reduced down to micrometer size, FREP is largely increased up to several hundred of gigahertz, which is similar to the 6G wireless carrier frequency. Next slide shows the principal operation for photonic terahertz generation. Microcomb generates OFC spectrum with FREP over 300 gigahertz. Optical bandpass filters extract two adjacent OFC modes, Nu1 and Nu2, from microcomb. The resulting two OFC mode generates with a frequency spacing of FREP generates the optical bit signal in time domain like here. The bit frequency or envelope frequency is exactly equal to the FREP. Then the optical bit signal is converted into the terahertz wave by photomixing with a UTC PD. The resulting terahertz wave has a frequency of F terahertz, which is exactly equal to FREP. In this way, the low phase noise property of FREP is transferred to terahertz wave. We here use a silicon nitride micro ring resonator with a FSR of 560 gigahertz and a Q factor of 1 million. After passing through an optical frequency modulator and EDFA, the pump light from the CW laser is coupled into the micro ring resonator via the evanescent wave. By rapidly detuning the wavelengths of pump light across the resonance of micro ring resonator by optical frequency modulator, the stable solitone comb is generated with at the power of a few milliwatt, like here. The resulting solitone comb is further amplified to a power level of 30 milliwatt by another EDFA, which is sufficient to drive the UTC PD. We next generate the 560 gigahertz terahertz wave by photomixing of 560 gigahertz spacing microcomb, free-running microcomb at the telecommunication band of 1.5 micrometer. Then the microcomb is fed into the UTC PD for generation of terahertz wave with F terahertz. Terahertz wave is propagated in free space and was detected by subharmonic mixer with a local oscillator with a FLO. Right shows RF spectrum of heterodyne bit signal. The RF bit signal appeared at 150 megahertz. From this equation, we determine the F terahertz to be 560.03 gigahertz, which is equal to FREP. Lower shows Lower compares phase noise between FREP and F terahertz indicated by red and blue color. Phase noise spectrum of F-rep and F-terahertz are almost overlapped with each other, indicating that the photomixing of UTC-PD does not spoil the low phase noise of F-rep inherent in microcomb. We here evaluated the free-running microcomb. We next stabilize the F-rep in microcomb based on the TWDI, so two wavelengths delayed self-heterodyne interferometer like here. The microcomb is divided in two fiber paths. One is frequency shifted by AOM, indicated by red dashed line, and the other is time delayed by a spool fiber without the optical frequency change indicated by red solid line. And then so they are combined again. So the optical bit signal between the microcomb and its replica shifted by AOM. So the red solid line and red dashed line are generated. Two optical bandpass filters with a different passband extract the pair of optical bit signal at the two different wavelengths, like here. Their bit signal are detected by photodetector and their further are mixed with each other, like here. The resulting secondary bit signal is used for the current control of pump laser diode power in microcomb. Left shows a comparison of phase noise between free running and stabilized F-rep. The phase noise of the stabilized microcomb was largely reduced down to the minus 100 dBc per hertz at the frequency offset of 10 kilohertz by active control. The right shows a comparison of phase noise between stabilized F-rep and F-terahertz. Even in the stabilized solid microcomb, the phase noise curve of F-terahertz is completely overlapped with that of F-rep, indicating that no additional phase noise via photomixing process in UTC-PD. In this way, the ultra-low phase noise of F-rep in stabilized microcomb was successfully transferred to F-terahertz. So that this level of phase noise cannot be achieved by electronic approach. Only the photonic approach using a microcomb can be, or OFC can be achieved, can achieved. Unfortunately, the optical signal to noise ratio of microcomb is limited by ASE background, resulting from the EDFA. To enhance the OSNR of the microcomb, we applied the optical injection locking technique, OEL, for the microcomb. We use the solid-on microcomb as, we here use a solid-on microcomb as a master laser with a high accuracy but a weak power, whereas DFB laser as a slave laser with a high power but unstable. By tuning the wavelengths of the DFB laser close to one mode of microcomb, DFB laser is passively phase locked to the microcomb mode, namely optical injection locking. As a result, advantage of them can be combined, namely high accuracy and high power. Upper left shows a comparison of phase noise curve among the free-running slave laser, microcomb, and OEL slave lasers. Importantly, the phase noise curve of OEL slave laser was overlapped with that of microcomb. So the low phase noise transfer was successfully achieved. Lower left shows a comparison of optical spectrum between microcomb and OEL DFB laser indicated by blue color, red and blue color. Whereas their optical frequency of DFB laser were completely equal to the microcomb mode, the pair of the OEL-DFB laser achieves the OSNR of 50 decibel corresponding to the 20 decibel enhancement. In this way, the optical amplification and low phase noise transfer were achieved simultaneously. The next slide shows the experimental setup of terahertz wireless communication. We here use a free running solid microcone with a FREP of 560 gigahertz. Then the microcone was fed into the optical setup for OEL. The resulting pair of OEL-DFB lasers, so OEL-DFB1 and OEL-DFB2, were used for the unmodulated neuron light and the modulated neutral light, like here. The neutral light was modulated by a combination of lithium niobate modulator and AWD. Then they were combined again and amplified and fed into the UTC-PD. The resulting terahertz wave has an optical spectrum like here, composed of a single unmodulated component and a double sideband modulated component. The terahertz wave was detected by Schottky barrier diodes. The detected bit signal between them was measured by real-time oscilloscope. We first demonstrated the on-off keying data transfer at the 560 gigahertz. We here compare the optical spectrum and eye diagram of 1 gigaball OK signal between OEL and no OEL. In the case of no OEL, AC background limits opening of eye pattern. So in this case, the corresponding bit error rate was remained around the 10 power minus 8. However, in the case of OELs, optical spectrum indicates the no AC background, and eye pattern of 1 gigaball was clearly confirmed. Corresponding BER was here, so which is close to error-free communications. We next demonstrate the phase shifting keying data transfer at the 560 gigahertz. So this shows constellation diagram of 1 gigaball BPSK and 2 gigaball QPSK. In both of them, isolated symbol indicated by red color clearly appeared, indicating the successful data transfer. The corresponding EM values were around 23%. In this case, the error-free communication can be achieved by help of free forward error correction. Finally, we demonstrated the quadrature amplitude modulation data transfer at 560 gigahertz. In the case of 1 gigaball 60 CAM, the isolated symbol disappeared due to the low signal-to-noise ratio. However, in the case of the 0.4 gigaball 60 CAM, 60 symbol clearly appeared. The corresponding EVM was 8%, indicating the error-free communication can be achieved. Finally, we demonstrated the present talk using this slide. We demonstrate the Photonic 6E wireless communication based on the Photonic terahertz generation and Photonic terahertz modulation and demodulation. So enabling the generation of low phase noise terahertz wave and advanced modulation and demodulation with photonics. We are also investigating the photonic terahertz detection based on the carrier conversion from F terahertz optical region, enabling the seamless connection to optical communications. So the Photonic 6E based on them 3E technique. This technique will satisfy the requirement of 6E and beyond 6E. Thank you for your kind attention.